Hi everybody, it's Professor Mitchell, and we are now finally starting actual trigonometry. This is the beginning of chapter 4, and this section is on angles and radian measure. Corresponds with your assignments 10 and 11. 10 to watch the video, 11 to do the homework. So in this section, we're doing all of these things. A new chapter always starts with a lot of vocabulary. Then we're going to get into degree measure, radian measure, converting between degrees and radians, drawing angles, finding coterminal angles, and we'll wrap it up with finding the length of a circular arc. Okay, so here's our vocabulary. So an angle, I mean, everybody can picture what an angle looks like. An angle consists of two rays. So these half lines are called rays. This is a ray over here. This is a ray over here. One ray is called the initial side of the angle. The other ray is called the terminal side. So your angle is formed by going from the initial side to the terminal side. So in a lot of situations, it does matter which side is the initial and which side is the terminal. All right, in this case, if I switch the initial and the terminal, then the angle would go in the opposite direction. And we'll get more into that later. The point where the initial side and the terminal side meet is called the vertex of the angle. Okay, so very, very often in trigonometry, we want to put our angles in standard position. Standard position means that the vertex is at the origin, at the point 0, 0, and the initial side of the angle lies along the positive x-axis. Okay, so here is a picture of an angle in standard position. This angle is called alpha. So that little symbol right there is the Greek letter alpha. You'll find that angles are often named after lowercase Greek letters. So the most common ones are alpha. This one over here is theta. And the other one that we use sometimes is beta. Okay. So here's another angle in standard position. And this time we went in this direction, in the clockwise direction. And the terminal side of this angle is over in quadrant 3. So those are a couple of examples of angles in standard position. Okay, so here are the same two angles. And so now they want to make the distinction between positive and negative angles. A positive angle has a counterclockwise rotation, which sounds like maybe it's kind of backwards. Why wouldn't they have made clockwise be positive and counterclockwise be negative? Well, there is a good reason for it, I promise. So positive angle means counterclockwise. So angle alpha would be a positive angle. Angle theta is a negative angle because it was generated by going clockwise. Okay. And then to wrap up the vocabulary, quadrantal angles are angles whose terminal side lie along either the x-axis or the y-axis. So just a sneak preview, quadrantal angles are multiples of 90 degrees. Okay. So if this was my initial side, that puts me in standard position. If I were to stop here, that would be 90 degrees. I'd be along the positive y-axis. If I stopped here, that would be 180 degrees. Puts me on the negative x-axis. The angle they drew is 270 degrees, and the terminal side of that angle lies along the negative y-axis. All right, continuing with the vocabulary, it's likely that some of these terms are familiar to you. Angles are measured by determining the amount of rotation from the initial side to the terminal side. So as you likely know, a complete rotation of a circle is 360 degrees. So if you cut your 360-degree circle into quarters, you get some of your different kinds of angles. So an acute angle is an angle that measures less than 90 degrees. So imagine if your angle was drawn in standard position, and I made all my angles positive, then your acute angle, the terminal side, would be in quadrant 1, right? A right angle measures exactly 90 degrees, so that's an example of a quadrantal angle. And then an obtuse angle, the terminal side would be in quadrant 2, okay? And a straight angle is, well, it's the same thing as a straight line, okay? Measures 180 degrees. As far as I know, there are no special names for angles that land in quadrant 3 or quadrant 4. Okay, but we do have these names for an angle in quadrant 1 would be acute, an angle in quadrant 2 would be obtuse. All right, so it turns out in calculus, it's very important when you're doing certain kinds of problems to measure angles in radians instead of degrees. So on this slide, we have the definition of radian measure. So imagine you have a circle and you have an angle that's cutting out part of that circle. The definition of the radian measure of that angle is you take the length of the intercepted arc, okay, so imagine walking along the outside of the circle, and then divide by the radius of the circle. And that gives you the radian measure of the angle. Radians are an alternative to degrees, and it turns out they work better in calculus. So one of my goals in this course and in pre-calc especially is to try to get you to think in radians, all right, and not always have to go back to degrees. Okay, so the definition of 1 radian, this picture kind of captures it. If your central angle, so this is what I meant by a central angle here, if the intercepted arc happened to have the same length as the radius of the circle, then that angle would be exactly 1 radian. It turns out that 1 radian is about 57 degrees, and in a little while you'll see where I get that from. Okay. So that's the definition of 1 radian. This, I think, is just exactly what I said a couple slides ago. I think this says exactly the same thing. So again, the definition of radian measure is you have this central angle. To find the radian measure of the angle, you divide the length of this arc by the radius of the circle. All right, so now we have an example of that. So suppose that the central angle of a circle has radius 12 feet, so it's a pretty big circle, intercepts an arc of length 42 feet, and they want to know what is the radian measure of that angle theta. So that's a really simple calculation. Just remember that the radian measure is the length of the arc divided by the radius. So the length of the arc is 42 feet. The radius is 12 feet. I like how they did this. So they canceled out the dimensions of the length of the arc and the radius, because what they're trying to stress is that radian measure is what we call a pure number. It does not have any units attached to it. So if you tell me that an angle has measure, let's say 2, it would be fair of me to assume that you must mean 2 radians, because if you meant 2 degrees, you would have had to put a degree symbol, okay? Radian measure is a pure number. It does not have any units attached. All right, so now we get into converting between degrees and radians. So to convert degrees to radians, you multiply your degree measure by pi over 180 degrees. And the reason that that works is because 2 pi radians corresponds with the whole entire circle. All right, that has something to do with the fact that the circumference of a circle is 2 pi r. Okay, so imagine that this had started out saying 2 pi radians over 360 degrees, and they just took out the common factor 2. Okay, So to convert degrees to radians, you multiply your degree measure by pi over 180 degrees. And to go the other way, to go from radians to degrees, you multiply the radian measure by 180 degrees over pi. Okay. Now, I've always worried a little bit that students might have trouble remembering, okay, when do I do pi over 180 degrees and when do I do 180 degrees over pi? Well, there's a way that I think is helpful to decide which one you should use, and you'll see it in the examples here. So for example, if I want to convert 360 degrees to radians, here's how I'm going to do that. I am going to multiply my degree measure by pi over 180 degrees. And the trick for remembering that it should be pi over 180 degrees and not the other way around, just think of the degree symbols. Oops, forgot to hit pen. Imagine the degree symbols canceling each other out. And hopefully that will help you remember that when you're trying to go from degrees to radians, you have to put the 180 degrees on the bottom because that's how you get rid of the degree symbol. Okay. And then I did not show all my work here, but that simplifies to pi over 3 because I also took out a common factor 60. Here, I'll throw that in here while I'm here. So 60 divided by 60 is 1. 180 divided by 60 is 3. So that's how you get pi over 3. Okay. The next example, we want to convert 270 degrees to radians. So if you're watching the video, I'm going to let you pause the video and try that one. All right, so 270 degrees, it works exactly the same way. Because you're trying to get rid of degrees, you multiply by pi over 180 degrees. And once again, your degrees will cancel out. Okay. 270 and 180 have a common factor 90. So when you do 270 divided by 90, you get 3. When you do 180 divided by 90, you get 2. So that's how you get 3 pi over 2. And then the next example is more of the same thing. Really, the most important thing I can point out about this example is just make sure that when the degree measure is negative, that the radian measure will also come out to be negative. Be careful you don't lose that negative sign. Okay, so you see how I did that here. Again, the degree symbol, whoops, cancels out. And 300 and 180 have a common factor 60. So 300 divided by 60 is 5. 180 divided by 60 is 3. And that's how I get negative 5 pi over 3. All right, so now we get into converting radians to degrees. So the way that you will know whether to use pi over 180 degrees or 180 degrees over pi is that radian measures do not have a degree symbol in them. And the answer that you're trying to get does have a degree symbol. So that's why we have to use 180 degrees over pi, because that brings in the degree symbol. So what's going to happen here is that pi will cancel out and the degree sign will come in, and then I can just simplify the fraction because 4 and 180 are both divisible by 4. So 4 divided by 4 is 1. 180 divided by 4 is 45. So that's how we get that that's 45 degrees. Okay. Next example, and I'll ask those of you watching on the video to pause and try this one yourself, would be negative 4 pi over 3. Okay, so hopefully you had a chance to try that. So we're converting -4π/3 to degrees. So just like in the last example, I'm going to multiply by 180 degrees over pi. Number one, make sure you keep your negative sign. Once a negative angle, always a negative angle. And because my radian angle had pi involved, that, whoops, need to bring up my here. Okay. The pi is going to disappear. The degree symbol is going to come in, and 3 and 180 are both divisible by 3. 3 divided by 3 is 1. 180 divided by 3 is 60. 4 times 60 is 240. So -4π/3 in radians is the same thing as -240 degrees. Okay. And that brings us to this kind of weird example. Once in a while, you will get a radian angle that does not have pi in it. And what that usually gives you is a sort of messy degree angle. Okay. But you're going to start off doing the same thing you always do when you're going from radians to degrees, is you're going to multiply by 180 degrees over pi. All right. And what I'm doing off to the side here is I'm bringing up my calculator because most of the time when you have a weird angle like that, 6 radians, instead of leaving it like this, we will normally, or we may want to know, okay, well, about, you know, approximately how big of an angle is that? And so 1080 divided by pi is approximately, let me see, get my pen here, is approximately, I just asked the calculator, 343.9 degrees. It might be 0.7. I used 3.14 because the only calculator I have within reach is my phone. I don't know if that has a pi button on it. All right, but that's pretty close. If I was trying to draw a picture, for example, that would be perfectly fine. And I have